Good morning, good afternoon, good evening, wherever you are. Welcome to this SEGGER webinar on recording and analyzing the runtime behavior of embedded systems. I'm Axel Wolf, and I'm SEGGER's FAE for the West Coast of the United States, located in the California Bay Area. If you have questions during the webinar, please type them into the questions box and we will address them either during the webinar or in the Q&A session at the end. So let's get started. Alright, so this is the agenda for the next hour or so in this webinar. I'd like to start off with a really quick introduction to SEGGER as a company, just in case you're not so familiar with who SEGGER is or what SEGGER does. Then I'll start talking about a common problem that you might be facing when you're developing for embedded systems, and that is how to keep track of everything that's happening on the system. So we'll take a look at the problem, and then the various components that are needed to solve that problem, and then we develop and take a closer look at the solution. And that'll bring us to the SystemView live demo. That's going to take us about 15-20 minutes. After that, we'll take a look at how to start using SystemView yourself. If you liked what you saw and you would like to try it out, then those 10 minutes I'll show you how to get started. Then we'll have a 5-minute summary, and then we'll have some time at the end for the Q&A. Okay, just a really quick introduction to SEGGER. We're a global development tools company. We're about 60 people now, and we've been around for quite a long time, over 28 years now. Our headquarters are in Monheim, Germany, that is close to Düsseldorf. But we also have offices throughout the world. One is on the East Coast of the United States in the Boston area, and the other one is in California, where I'm sitting right now. And we also just recently opened our China office in Shanghai. And we have worldwide distribution as well of all of our products. So these are the 4 pillars, if you will, of what SEGGER does. We have one pillar that is the embedded software, so that's everything that goes and runs onto on the actual target device. So all the embedded software. Then the next one is the debug probes. We're pretty well known for the J-Link, which is pretty much the de facto standard debug probe in the embedded industry. So you've probably seen one, used one, seen somebody else use one. So it's very, very common, and we've been developing and refining the J-Link probes for 15+ years now. We also have a line of production programmers called flashers. So those are good for volume production and just programming your target devices once everything is done. And we also have a line of software tools that make it easier for you to develop and debug your software. And of course, one of them we're going to take a look at today, which is SystemView. So let me just give you a quick overview on the embedded software that we have. We do offer, which is software that's very typical that you need for a modern embedded system, for example, a real-time operating system. So ours is called MBOSS, which is also available in a safety certified version, which is MBOSS Safe. You probably need a file system. We have mFile for that. We have all kinds of stacks and libraries that you would need for networking, especially important for IoT devices these days. We offer USB device and USB host stacks. We offer other bus systems as well, like Modbus. Security is obviously a big topic these days, so we have a digital signature suite, and we have a cryptography library, and we offer a bootloader, which is mload, and we have some embedded compression technology, which is mcompress. And of course, also very important is graphics. So we have MWin, which is our graphics library, and you can use that if you have need for a graphical user interface. And as I mentioned, some tools that we have that run on the host. Embedded Studio is our IDE. Ozone is our standalone debugger. SystemView is our recording and analyzing tool that I'm going to introduce to you today, and then AppWizard is our GUI development tool for creating MWin GUIs. Okay, so as you can see, there can be lots of things going on on the embedded system at the same time, and the big question is, how do you keep track of everything that's going on, because there's just so much going on these days. And if you're just using regular debugger, just basic debugging, your insights into what's going on are fairly limited. So just a regular debugger connection doesn't take care of questions like the ones I'm posing here, like how do you make sure your system works as you designed it? How do you make sure you're getting rid of any inefficiencies that might be in there? You might be dealing with some resource conflicts or other unintended interactions, so it would be good to show those or to visualize those. Just in general, it'd be nice to get a visualization of your application as it's running, so in real time. But obviously, with minimal impact on that real-time behavior, that's of course an important point. And then obviously, it would be nice to be able to record all that and analyze it offline. And ideally, also, of course, you would not want to spend any additional port pins or hardware on this, other than the debug probe that you probably already have to connect to your target. So basically, to solve this problem, there's three elements that are needed. First, you need a way to collect that information that you're interested in on the target MCU. Then once you collect that, you need to extract it. So you need to get it out of the MCU via the debug probe over to your host computer. But obviously that needs to be happening very fast at high speeds and without, like I said earlier, having an impact on your real-time behavior of your target. You don't want to disturb that. And once you have the target or the information over on your host from the target, then you need to display it and visualize it somehow. And it shouldn't really matter if you're on a Windows machine or a Mac or a Linux box. So if we're taking a closer look at this, then I have here the target system on the left and then the host system on the right. So you have your embedded application that's running on your target system, and that is creating all kinds of events like user events and printfs that you might have in there. Your RTOS, when it's switching tasks and executing things, it's creating a lot of events. And then obviously any kind of middleware you might have running on it, USB stacks, networking stacks, those are creating lots of events. So what needs to happen is these events need to be collected. So via an API, the data needs to be collected and then passed over to an API that is responsible for the extraction of the data. And that would put that data into a data buffer on the device in the RAM. And from there, the debug probe will have access to that, And on the target side, the debug probe DLL will take care of the connection to the target, obviously, and then pass the data up to the DLL that's responsible for the data extraction, and then pass that up to the visualization and analysis tool. So basically from SEGGER, the components that we came up with to solve this problem or to implement the solution, I will introduce to you now. The first one is that I want to mention is the one we use for data extraction, and that is what we call RTT, SEGGER Real-Time Transfer. So RTT is free SEGGER technology for interactive user I/O and embedded applications, and essentially it combines the advantages of SWO and semi-hosting, and it's doing so at very high performance. So it allows you to do two things, basically. It allows you to output information from the target microcontroller, but also the opposite, sending inputs down to the application, doing so at a very high speed and with minimal impact on the real-time behavior of the target. You can have multiple up and down channels, and actually the number of channels you want is configurable at compile time. And you can use RTT with any SEGGER J-Link debug probe, but it has to be a J-Link. And any processor that allows for background memory access. So usually those are your ARM Cortex-M, Renesas RX targets. Those allow these background memory accesses that we need. But there's, in case you're interested in RISC-V, there's also a way to do that now on the RISC-V devices. The caveat or the prerequisite is that your RISC-V device supports or has implemented the system bus access. If that is implemented, it's optional, so it's not in every device. But if that is present, then we can run RTT, and that means we can take advantage also of SystemView. So just take a look at RTT Performance real quick. So we developed RTT because we were not happy with the existing solutions that were out there. And we wanted something that was much leaner and much faster. So we can actually output an average line of text in less than a microsecond. Essentially just a single mem copy. So here's an example for an ARM-based target. You might be familiar with semi-hosting. It's a very common method of exchanging information between the target and the host. But as you probably also know, it's very slow, and it uses a lot of additional, brings in a lot of additional code. SWO was definitely a improvement, but for what we wanted to do, it was still too slow. So we came up with RTT, and you see that it even a lot faster than SWO. So just by the way, this is running on, or these numbers are from a Cortex-M4 at 168 megahertz. Obviously, the performance varies with what core you have and how fast you're running it. But just to give you an idea of the performance. So how does RTT work? Well, to manage those data reads and writes, RTT is using some elements in the target's memory. One is a control block structure, and then a number of buffers, one buffer per channel. And the RTT control block essentially contains an ID that makes it locatable for the J-Link that is connected. So J-Link can find that control block in memory, and then also a ring buffer structure for each available channel, and so that describes the channel buffer and what state it's in. So just to give you a broad idea of how that works on the target side, in terms of transfer speed, so there's some factors that have an impact on the transfer speed, and one is the target buffer size, which we have here. Obviously, the larger the target buffer is, the less overhead you have, and the faster your transfer speed is. And also the target interface speed. So basically, how fast the debug probe, or the J-Link in this case, and the target exchange information, that also has a big impact on the speed. And so again, here we have the buffer size, and here is the transfer speed. And then we have that for 3 different probes. The blue line, the lower line here, is for a regular J-Link version 10 with 12 megahertz target interface speed. And you can see that even with a very small buffer of 512 bytes, you can still get like half a megabyte per second. That's just with the regular J-Link and a very small buffer. And if you have a higher end J-Link, like an Ultra Plus or a Pro, at different speeds here, then you can see you can achieve a lot higher transfer speeds, especially if you're also able to increase the buffer size, because you're running on a target that you have that luxury of having that extra RAM for these buffers. So now we're going to talk about data collection and visualization and analysis. So this is where SystemView comes in. It's a toolkit we developed for the visual analysis of embedded systems. So what it allows you to do is capture all these user events, all kinds of events like timers, interrupts, API calls, tasks. And we designed it to be minimally system intrusive, so not to mess with the real-time behavior. And you can use that no matter whether you're using an RTOS or not. So you can use it with an RTOS or just bare metal. And so the idea, of course, is to gain a deeper understanding of your runtime behavior and gaining some nice insight into your application and how it works. And obviously, especially if you have a lot of tasks and a lot of events, that makes it even harder to keep track of everything. So that makes a tool like SystemView particularly useful. And there's 2 parts to SystemView. One is a visualization recording application or program that runs on the host, and we have that for Windows, Mac, and Linux. And then there's some embedded code that you need on the target system, as alluded to earlier in the slide that showed the structures. So that is the SystemView software module, and that collects and formats the data that it gets from the various events, and it passes it on to RTT to be extracted from the target. So what are the benefits that SystemView offers you? Well, if you have questions like, or if you'd like to know which interrupts, tasks, and software timers have executed, how often and when, and how much time they use, then you can get that from SystemView. And it just gives you an idea of what happens on the target, which interrupt has triggered which task switch, which interrupt and task has called which API function, and so on. So we'll see that all a lot better later in the live demo. This is just a little preview of what SystemView can do. So here's how SystemView and RTT work together. Again, these events, or these elements here of your embedded applications, they create all kinds of events, and they call the SystemView functions to pass that on to the SystemView API, for example, when an interrupt starts or an interrupt ends. And in turn, SystemView passes these events on to RTT, and it also gives it a highly accurate timestamp that goes with it. And these timestamps are configurable, and they can be very, very accurate. So as accurate as 1 CPU cycle, which if you're running at 200 megahertz, that's about 5 nanoseconds, so that's pretty small time frame. And then RTT then stores the collected data in the target buffer, and that allows the collected or the connected J-Link to continuously record what's going on the system. There's also another mode that's called single shot recording, but usually the better option is to just continuously record what's going on, and then you can analyze that offline by just analyzing the recording. So this is how that works. You might ask, what kind of resources is that taking up on my target side? And again, we try to keep that to a minimum. So the amount of flash or ROM that's required for RTT and SystemView is actually less than 2 kilobytes. So it's not a lot of code space that you need for that. And usually 600 bytes of RAM should be enough for a typical system for continuous recording. Obviously, like I mentioned earlier, if you have more RAM available, you can increase the buffer size and increase your throughput a bit, but typically 600 bytes are fine. You might ask how to determine the size of the buffer, and that is essentially depending on the time that you need to record and the amount of events that you have. Obviously, the more time and the more events, you should increase your buffer size. And we have some formulas that help you determine what the ideal buffer size is. And in terms of overhead, we looked at this carefully, and basically, again, in the example where you have a 200 megahertz CPU and a system that has about 10,000 events per second, we determined that there's less than 1 microsecond of CPU time that is required for collecting all this data, which is essentially a 1% overhead. So we think that is acceptable for the insight that you're gaining from spending those 1%. And the nice thing about it is that other than the debug probe you already have, there's no additional hardware or pins required. So as you probably know, if you're doing tracing, instruction tracing with a trace probe, like JTrace Pro that we also offer, you do need these additional trace data and trace data pins and trace clock pin, and those pins are often not available or they're not accessible, so that can be a bit of a problem sometimes. But with SystemView, since you're doing this with instrumentation of your code, there's no additional hardware or pins required, which is nice. So let's just take a quick look at the SystemView Host application. So we're having different windows here that show what's going on. The first window here is a list of all the events. The second one is some runtime information that shows you the variance of your different tasks that are executing. We have a terminal that can give you terminal output, messages, or other information that go through the terminal. The key component is the timeline that you see here with number 4. So that gives you the exact information of the task switches and the events and how they correlate with each other. Number 5 is the context information. So I'll show you later what's in there in the live demo. And then you also get a nice indication of the CPU load. You can basically see that color coding, which corresponds to the various tasks that are happening. And the last window here is the system window, and that gives you all kinds of system information. So let's move on to the live demo. And the hardware setup that I have on my desk here, I have my PC on which I have Embedded Studio, which is our IDE, and of course I have SystemView installed. And I downloaded the SEGGER eval software package for SEGGER Embedded Studio for my target board, which in this case is our mPower board with Cortex M4, but I'm just using this as an example. We have, as I'll show you in the end, we have example software packages and MBOSS trial versions for lots and lots of different boards. So this is just the one I picked for this demo. And then in the middle I have a J-Link Pro, which is one of the higher end J-Links that has up to 50 megahertz of target interface speed. And so that is connected through USB to my host computer, and then the J-Link itself obviously is connected to the debug interface here. So this board actually also has a J-Link on board already, but this is obviously just a regular J-Link with a limited target interface speed, so I did not choose that for this webinar because I wanted to show you higher end. So if you have a board that has a J-Link on board already, you can definitely use SystemView. Whether you're going to get any overflows or not will depend on what I already mentioned earlier, like the target interface speed, how many events you have. I wanted to show you the highest performance, so I chose my J-Link Pro. So that's my hardware setup, and we can switch over to the live demo. So first thing I'm going to bring up is Embedded Studio. Like I mentioned, that is our own IDE that we use for embedded development, and I loaded up the eval software package for this board. And you can see in these eval software packages we cover a lot of our middleware as well as our RTOS, which is MBOSS. So there's lots and lots of examples in here that you can run on the target for the file system, for the GUI, for the USB, for the Ethernet. So there's lots of different examples in here, and you can switch them in and out and build them and run them on your target. That's how our eval software packages are structured. So I want to start with, I'm going to show you two examples. One, a very simple one, so we get the hang of things, and then I'll switch to a more complex example. So I'll start just with a regular LED blinking example. So I can, I have that currently as the as my file to be compiled, and I can just check my options real quick on my debugger. So I'm connecting with SWD and the highest possible target interface speed, which is 50 megahertz. But first I can build my example, and then I will use J-Link to download that. So I can start a debug session, and we are stopped at main. So once we have reached main, we can run the application, and I can show you what's happening on my target board. Let me bring that up real quick on my webcam. So here's my J-Link Pro connected to my target board, and I have these two LEDs that are blinking. One is toggled by the high priority task, and the faster one and the slower one is toggled by the low priority task. And so those are the only two tasks that are running right now. And obviously it would be nice to be able to visualize that. So let's bring up SystemView, and let's double check our recorder configuration. We want to record through J-Link. This is our target processor that we're connected to through SWD at 50 megahertz. And I am telling SystemView to automatically detect the RTT control block. So everything's set up, so we can actually just start the recording. So SystemView will start, and the recording is running. So we're running live, and the events list is filling up. As you can see, here's the number of events. So since we started recording, we've had like 80,000 events already. The timestamp is here, the type of event is here, and some details are being offered here. Then in the timeline actually acts like an oscilloscope in a way for your embedded application. You have all the different tasks over here. So like I mentioned, you have, in this application, we have a high priority task and a low priority task. And on top of that, of course, we have our scheduler, our system tick, and then we have an idle task that runs when nothing else is going on. So now what you can do is use the trigger function, and you can trigger on different events. So for example, let's say I want to trigger on the high priority task when it is running. So now I'm triggering on my high priority task whenever that is running. So I can see that here. And if I actually zoom out a little bit, we get another better idea of what's going on. So every 1 millisecond, we see that there's a system tick, a little less than a millisecond, but about every millisecond we get a system tick, and every so often the scheduler will run after the system tick and would determine which task is ready to run next. And in this case, since we're triggering on the high priority task, this is what we're seeing. High priority task runs and passes it back to the scheduler and then back to idle. But actually sometimes you also see the lower priority task being executed right in the back of it, because it probably had to wait for the high priority task to be finished. And in here, in these blocks, you actually see the events that are happening. For example, here it's the OS tick handle function is called in the systick. And then here in the high priority task, you see the events here, OS task delay, and this is just task run. So all this is happening, and we could also trigger on different events like interrupts and markers. But again, this is there's not all that much happening in this application. But again, you can see what is happening. So let's take another look at the different windows to finish this tour. So here, this is the runtime information. So that gives you an idea about the distribution, the timing distribution of the various tasks. So how far apart they are in terms of timing. So it gives you a good indication of your how well your embedded system is doing. Looks like the scheduler has the biggest variance here. This is the window that shows you the CPU load. So depending on how I zoom in and out here, you get the color-coded CPU load for the time frame that we're looking at. And of course, in our case, red is the system tick, the screen is the high priority task, and so on. Down here is the context information. I didn't want to do that. So that again shows you the different tasks that are running, what type it is, if they're using any stack, how many activations they've seen, how much time they were blocked, total runtime, how much time they were interrupted, what CPU load they place on the CPU, which is great for profiling, and then some other timing information. And the last window here is the system window, so that gives us some nice information about the overall system characteristics, like we can see how fast our CPU is actually running, the duration of the recording. So we've been recording for about 5 minutes. We've recorded 1,250,000 events. So that is about 4,000 events per second. So far we haven't had any overflows, so that's really good. And just some other statistics like the number of tasks, how many interrupt service routines, how many timers, markers, and so forth. So this is what SystemView can offer you in terms of visibility into your application. And again, this is a very simple one. So let's stop this recording. But what I mentioned here is once you've recorded a certain amount of time, you can save that for analysis later. And obviously we can look at the complete recorded history, and we can go, we can zoom into any part of the recording and see what was going on. The events window and the timeline are synchronized, so I can, if I step down, if I arrow down in my events window, that will also advance the timeline, and the same thing the other way around. So I can step through my timeline, and that also advances the event. So that's always in sync. So that makes it easy to later analyze the recording. And again, you can save that and bring it back up at any time later on. So let's switch back to my IDE, because we want to actually stop executing here, and I want to run something a little more challenging. So the way you switch out applications here is, or demos, is the one you don't need. You just exclude it from the build and you include the one you want to run. So in this case, the SEGGER demo is like a collection of various demos that we have for various peripherals and various parts of middleware. So I can just include that in the build and rebuild that application for this different demo. And then I have to obviously start a new debug session, and my JLink is programming that, but it's so fast I can't even show you that. So again, we're sitting at main, and let's run this. And so in this case, we are getting some other activity. So at this time, we have activity on the LCD, we have USB running, we have Ethernet running. So I have a Ethernet cable actually connected here. So there's lots more going on in this demo than just the 2 blinking LEDs that you saw earlier. So let's switch over to SystemView and record that. So the target is exactly the same. So all I have to do really is to start the recorder again, and it will give me the updated information. So here now I see I have a lot of different tasks, not just 2, a bunch of interrupt service routines, and but the principle is the same. We're running the application, but now we're recording actually a lot more events, so almost twice as many. So 11,000 events per second are currently being recorded. but the idea is the same. We can trigger on certain tasks, for example, when the main task is running, and that will determine what I see in my timeline. So where's the main task? Hold on, I gotta make some room here. So here's my main task, and I have all the, let's put that back here. You can rearrange these windows and undock them and redock them to just get the user interface just right. So now you get the idea that a lot more is going on in our system. I can zoom out a little bit, and we see that we have a lot less white space, which means a lot less idle task, which means quite a bit more CPU load, and we also see that in the number of events that we're recording. You might notice, so web server and FTP server, we have no runtime information, so these haven't been used yet. So what I can do is show you my system here and also bring up the website or a web browser here that I can access the web server that is running on the board through this Ethernet connection over here. And so, for example, I can do some simple sampling here. For example, through this interface, I can turn some LEDs over here on and off. So these LEDs are just turned off through the web interface. I mean, I turned them on, and you can now see that we have web server activity here that we didn't have before. So that just got triggered by me turning on those LEDs in the web server. So overall, I hope you get the idea of how SystemView can give you this important insight and analysis into your application, and how you can record that and then analyze later on, and just make sure that your timing is right, and everything is going well in your application, and you're not experiencing any hiccups. Okay, so we can stop this demo and we can go back to PowerPoint. So that was the live part of the demo. So if you're interested in how to use SystemView, you know the whole solution now. I don't think I need to spend a lot more time on this. So how do you get started? Well, how to add SystemView target system first. So as I mentioned, it is done with instrumentation. So you need to add a small number of files to your project and compile them with your application. And so if you're using an operating system and that operating system is already instrumented for SystemView, then you only need to call one function and you're done. So currently the real-time operating systems that support the SystemView instrumentation are SEGGER Emboss, which is our own RTOS, obviously, and then the Micrium, MicroCRS, and FreeRTOS as well. So if you're using one of these, then you're in luck because they are already instrumented for SystemView. If you have an RTOS that is not on this list, or if you don't even have an RTOS, if you're just running bare metal, then you need to instrument your code by yourself. So for example, essentially for every event or interrupt or function that you need to monitor, you need to add 2 lines of code that allows SystemView to capture that. So we have a nice wiki page that you can't click that link right now, I don't think, but you can just Google for SEGGER Wiki SystemView, then you can reach that. So here's an example for an interrupt service routine that could be monitored with SystemView if you don't have an OS. So when you enter, this is your interrupt handler. The first instruction is calling the SystemView API and say record the entry to the interrupt service routine. Then you have your regular function that your interrupt service routine would be doing. In this case, it's some ADC handler that's reading out the value. And then before you leave the interrupt service routine, you record another event. And so these are the events that then get captured and allow you to monitor your application with SystemView. And the complete API, you can check out our user guide, and that has the complete API in it. So if you want to really try it yourself, you can just go onto our website and download and install SystemView. We have what we call the SEGGER friendly license, and SystemView is covered by that. So you can download it and run it without any limitation and use it for non-commercial and educational purposes and for evaluation. So you don't need to register, you don't need to activate anything, and there's no limitation. You just use it under that license, and you can get started. So on the SystemView website, there is a download link right here, and you can download. And then if you don't have any hardware currently connected, you just essentially run the SystemView application, and then you open up one of the sample recordings. So you can go File, Recent Files, and there's a couple of, or like up to 4 examples here. You pick one, and you can start checking things out, just like I did right now. Obviously, it's not going to be real time, but you can look at all the windows. You can scroll through the recorded data and basically analyze that recording. If you want to do it on real hardware, then I invite you to check out our Emboss trial packages or eval software packages. So we have a section on our website that we call Evaluate Our Software, and we have software sample packages for a lot of different chips from a lot of different vendors. So you can click on the one that your favorite silicon vendor. So for example, if we go with ST, just for an example, then you will see a list of boards that we have example software for. So we have BSPs or complete projects available for a lot of different boards. So you pick one that you have maybe in your drawer or on your desk at the moment, and then you download the examples. So either it's going to be a complete SEGGER eval software package that like I was using, or it might be a Emboss trial package. But in either way, it's going to be suitable for SystemView. To build those examples, you also need to download Embedded Studio, which is coming under the same license. So just to evaluate it, you can use that SEGGER's friendly license, and there's no limitations code size wise or time limit wise or anything. You just download, install, and off you go. So the next one, of course, is the debug probe. So either if your board has a J-Link OB, then you're fine, obviously. If not, then you need to connect an external J-Link. Or if your board, for example, has an ST-Link or an NXP LPC Link 2, then you can actually replace those firmwares with a J-Link OB firmware. So we have links on our website, or actually not links, but utilities that let you replace the ST-Link or the LPC Link firmware with a SEGGER J-Link OB firmware. So you can make that ST-Link or LPC Link a lot faster And you can use all the SEGGER J-Link utilities under evaluation, obviously. So just to for you to check it out, how it feels to use a J-Link compared to some of these other implementations. Then you connect that board to your PC through either the external J-Link or the J-Link OB. You open up the SEGGER software package in Embedded Studio, you build it, you start the debug session just like I did in the example, and then you run the code. You switch over to SystemView, configure your recorder options, basically making sure you have the right chip selected for the target target interface, and the right speed. Start the recording, and off you go, just like I showed you in the demo. So I invite you to try that out and yeah, experience the benefits of SystemView. So that gets us to the end. Just as a little summary, how we saw how J-Link and RTT and SystemView work together to give us some nice real-time visualization and allow us to analyze our application's runtime behavior. We saw how you can record that and analyze it offline later on. And we saw that the nice part about it is that no additional hardware or pins are required, just some instrumentation in the code. And again, I want to stress that if you are designing, if you happen to be designing RISC-V SoCs, or you basically your company does RISC-V SoCs, I encourage you to include the system bus access block. So again, that takes care of the background memory access, and that allows us to run RTT and SystemView even on the RISC-V based devices. So again, it's an option, an optional feature, but we think it's well worth adding to gain that additional visibility. So just before we go to the Q&A, just some additional resources. Obviously, there's the SystemView webpage that you can check out. We have a nice user guide for SystemView as well as for J-Link, as well as actually for all our other products too. And you can also check out a video on SystemView that is online as well. So with that, I am at the end of the webinar. So I would like to thank you very much for your attention. And what I'd like to do now is take a look at the Q&A and see if we have any remaining unanswered questions, and maybe highlight a few questions that came in during the webinar. I see that my colleague Nino was already answering a lot of the questions, so thank you, Nino, for that. But we can probably, since only the person who answered or asked the question can see it, let me just pick a few out. So one question was, what is the ideal J-Link probe you recommend to get full advantage? I think I mentioned that you can use SystemView with a lower end probe, but the higher end J-Links with the higher target interface speed will give you better performance, and you can do more events. Let's see. Assuming the MCU has the necessary hardware support, can SystemView be used with any MCU vendor? Yes, you can use SystemView with any vendor. You can also instrument your non-RTOS application. And I also mentioned which RTOSs are actually currently supported. So that is MBOS, FreeRTOS, and MicroCOS. But it's possible to instrument all of them. Which processor families does SystemView support? Again, essentially any. Because what I did mention is you can also use UART and IP for the data transfer as well. I didn't mention that, but that's also possible. So let's see. What else do we have? How much stack does the SEGGER monitor program use? So the maximum is 510 bytes, but that's kind of the worst case. Usually that's less, and you can find some information on that in the manual. Does SystemView work with any other IDEs or only Embedded Studio? No, you can use any IDE or toolchain that you want. I just showed Embedded Studio because it's easy for me to build the example projects, but you can use whatever IDE or command line you want to build the project, as long as it has the SystemView instrumentation code. Can the record session go on forever? Well, technically, theoretically, yes, from a SystemView perspective, but from the host OS, at some point, the file is just going to get too big. So at some point, that will be an issue. Let's see. Oh, this is a good one. Is it possible to configure SystemView to generate a pop-up or any indication when some configurable conditions are met? In case I want to detect, for example, the order of execution my task was altered. And yes, the answer is you can create some user events that would allow this. So you can use it for that. And another question is, where is the SEGGER stub for supporting SystemView that needs to be added to the code? So all the SystemView and RTT target sources are provided with SystemView when you get that. And you can also find that on the SystemView download page. And then those can be used in any IDE that supports C code. Again, which RTOSs are supported? I mean, theoretically, any RTOS is supported. The question is which ones are instrumented out of the box, which is MBOS, FreeRTOS, and microCOS. But again, you can instrument it yourself if you have the kernel. And maybe one last question. What is the highest frequency interrupt that can be monitored? Is 10 kilohertz interrupt too fast? No, that should be no problem. As I mentioned, on a typical system, a SystemView event is about a microsecond. But obviously, the faster your target device, the lower that number is. So we'll just, in the background, continue to answer some questions if they come in. Otherwise, again, thank you so much for attending the webinar and for your time. And I would like to end the webinar. So have a good rest of your day, wherever you are, and stay safe. Thank you so much.